how do we dump onto the FPGA, how do we create complexity. Okay, tomorrow we'll be mostly concentrating on what are the application possibilities using an FPGA and what are the advantages of running applications on said FPGA. There are multiple just a brief introduction to Coral Technology. Coral Technology is working in 4 different areas. One is defense and aerospace, one is digital video broadcasting, next is high performance computing and higher education market. We are dealing with the higher education market right now in this segment. So we work in a lot of segments, and we also have Sandeepni, that is going to be the APT of AMD in India, which is authorized training partner for AMD in India. Okay, so we also work with other toolsets, Mentor, MathWorks, Ansys, Siemens, QT, downstream vendor. So yeah, as I told you, Sandeepni is the official training partner for AMD in India. We have done a lot of projects with in combination with the Educational Department of India, Government of India as well. So one of those recently we have done is a C2S program, Chip to Startup program, that throughout India more than 110 colleges have been a part of it. So moving on to today's session, so we are going to look at multiple architectures that we have when it comes to Xilinx FPGA and how do we go about the flow of designing an FPGA right from the scratch. We'll be looking at 2 different methods for today, the whole day I mean. One is going to be how do we start from RTL coding, and the second is how do we design using IPs. We'll also be looking at some of the features that are available to us from Vivado. How do we read power, what are the features that we have directly available, how do we integrate other available resources, how do we take out some reports that we might require while presenting a paper or to submit some documentation. Okay, so there are a lot of things that we can cover. So depending on the time and what is more interesting to the participants, we'll go with the. If anybody has any questions, you can stop me at any given point. I'm happy to help you out. Okay, so when we talk about the architecture, current version of Xilinx FPGAs, right? Overall, the current version of Xilinx FPGAs starts from something called as 7 series, series 7 FPGA. Okay, so this is the latest technology that Xilinx is working on. Okay, and this is the baseline. So on top of 7 series technology, we have a lot more of other technologies. What do I mean by other technology? Whenever we are talking about any kind of technology, we always try to see how small can we go. 45 nanometer, 28 nanometer, 26 nanometer, 70 nanometer, 11 nanometer. So we can keep going down. 7 series of architecture, we are working at 28 nanometer. And from there, we have other technologies which have a reduced size as well. This is the base that we are working with. So once we understand 7 series, rest of the architecture, rest of the technologies that we have are going to be built on top of the same technology. Okay, or the baseline is going to be the same. So in general, when we talk about FPGAs, there are a few resources that are something that is going to be in everything that we are looking at. There needs to be a set of logic resources. In the 7 series of Xilinx FPGA, they're going to be called as CLB. So the term CLB stands for configurable logic block. So inside this, we have a lot of other components as well, but on a whole, this is a block that can be configured for our requirement, either to store logic or to store data or to do process. So this is common all the way from the 7 series architecture to ultra scale plus. It can be MPSoC, it can be RFSoC. Wherever you go, the CLB at the core is going to be the same, but the functionality of the CLBs is going to vary. So when we talk about the 7 series architecture, we'll be looking at something called as slices. There are 2 different slices when we talk about the 7 series CLB. So each CLB has 2 different slices. One is going to be a pure logic slice, one is going to be a memory integrated logic, slice L and a slice M. So the slice L is purely only to store the logic, whereas the slice M, you can store either the logic or you can convert it into a temporary memory. It's not a dedicated memory, it's a temporary memory. This can also be called as DRAM, which is distributed RAM. You are storing small chunks of data throughout the available fabric of the FPGA using the memory function of that particular slot. So that is called as distributed RAM or distributed memory. This is good when we want to store some data, some intermediary data for faster process. You don't want to put it somewhere else where you might require some additional amount of time to go there, fetch that data, get it into your processor, process that and again store. Rather, you can store it in the same location. So this is one way that CLBs are useful. But when we go higher, when we go to ultra scale plus architecture, there we won't be able to see slice L and slice M. Okay, there is no different slices for logic and memory. There is only one slice. The advantage there is here in a CLB, we are looking at 4 different blocks of LUT, right? In 7 series, we'll be looking at 4 blocks of LUTs. LUT stands for lookup table. But in an ultra scale plus FPGA, we are looking at 8 LUTs. So both the slices L and M are combined and 8 LUTs are directly available to us on a single slice. There are no 2 different slices. There is only one slice. What happens to the RAM? What happens to the memory that I want to store? So I just told you that this particular slice M, the memory module, will be really helpful when you have some kind of intermediary data that you want to store for a temporary time, for a temporary purpose at a very short time, right? But what happens to my data when I go to ultra scale plus architecture? Why is there no intermediary memory or quick access memory there? Because what I've told you is this can be used as a memory. But when it comes to ultra scale plus architectures, ultra scale plus architectures, there we have something called as ultra RAM. So the slice M, which is purely for temporary purpose, has been replaced with something called as ultra RAM. That is a high speed memory modules available to us directly on the chip, on the silicon. So though the slice M is useful for us to store intermediary data because it is faster, again parallel processing of FPGA is also available there, right? So that is why it is faster. But we have replaced that with a dedicated source, right? Dedicated memory modules are replacing the slice M. So when we talk about multiple architectures and we start off with the basic, which is the 7 series FPGA, so all we are doing is building on top of the 7 series FPGA. Something is not working out, something is working out, we'll keep it, we'll change it, things like that happens. So understanding the 7 series architecture will give you a lot more flexibility, will give you a lot more power when you want to work on higher so yeah, as we have discussed, we have logic resources. The primary thing is going to be CLBs, configurable logic blocks. Then we have multiplexers, we have a we have memory modules. Yeah, so this memory is again different. This memory modules are going to be dedicated silicon memory. Yeah, those are the dedicated memories. That is what the memory here stands for. The block RAM is going to be a dedicated memory. Slice M is going to be a distributed RAM. That is something that we are creating for our purpose. We'll be interested in is going to be the interconnect resource. So we are doing something on the FPGA, but we need access to the FPGA from the outside world and we need to be able to access that FPGA. We interface the board with the outside world and vice versa. The next thing is there are a few more resources that are required for us on the board. Okay, they are not going to be something that we can completely access and reprogram. They are going to be some kind of resources that are purely taken care by the tool or the board in itself. So this is a set of resources that we'll definitely have on all the 7 series architectures, architecture based FPGAs. Okay, here we are purely talking about a pure FPGA. Okay, we are not discussing about an SoC here. Okay, this is purely the architecture for pure FPGA. So as we have discussed, we have CLBs, we have BRAMs, those are block RAMs, that is the dedicated silicon for memory. We have IOs, those are the input output pins. We have CMTs. CMT is going to be the clock management tiles. Okay, And we'll also have MGT, which is going to be management tiles, general management tiles. And if we go to higher architectures, right, we'll have dedicated management systems for multiple processors. In Versal, we can only access the board through something called as a management unit. As I've already told you, it is always going to be a step up from this. Along with that, we also have some resources that are going to be the buffers, clock buffers and DSP. So when we talk about the 7 series family, we have 4 subsections in that, and one sort of like a superset, that is zinc. Okay. So inside the 7 series family, we have Spartan, Arctic, Kintex and Vertex. Those are the 4 subfamilies that we have. And we have zinc, which is going to be an SoC, which stands for system on chip. So we have zinc, that is going to be the system on chip. Today we'll be working in this lab with a pink board, which is an SoC, right? It's a zinc based chip and it is following the architecture of Arctic 7 FPGAs. So what is an SoC or zinc chip is, we have the pure FPGA that we have already seen. This is a pure FPGA, and on top of this we have an added processor. On top of the pure FPGA, we have an added processor. Okay, that is going to be an SoC, system on chip. The processor that we'll be dealing with is going to be an ARM based processor. For 7 series architecture, mostly we'll be looking at ARM Cortex A9 processor, ARM Cortex A9 processor. And this particular board, the pink board that we'll be using, will have a dual core ARM Cortex A9. So we'll look at the we'll look at what is available on the processor in the afternoon session, because we'll be building a complete system then. Okay, but for the first session, we'll mostly be concentrating on how do we program an FPGA. So if you can open your laptops or the systems, the first thing we need to understand is how do I work on a particular board that I want. I'm just going to show you one small thing here. Everyone, if you can look at the monitor, okay, there are multiple boards that I can work with. Okay, I'm just not creating anything right now, but I just want to show you one thing. Okay, so when we talk about the FPGAs, when we talk about FPGA in general, it is not only that you need to use the boards as they come from the manufacturer, but you can also design your own boards for specific applications. If you are willing to go that route, you can do that as well. Okay, so the how do I target an FPGA? There are multiple ways to target particular FPGA, right? You can directly search for the chip and target the chip. One is going to be the parts and one is going to be boards. Okay, so as I've told you, you can directly target the chip using the part number of the chip, or you can take the board with the board files as a package and work on that as well. So if you're working with some boards that do not have a complete board support package, we can directly search for the part number and target the chip directly. So as of now, if you check your systems, board support package for pink is not installed. We're working on the pink Z2 board, but the board support package is not installed. So if you go to boards and search for pink, I have already installed it, but you will not be able to find the pink board directly. So in that case, you can directly target the part number as well. How do I find the part number? That's the next obvious question, right? So you can directly search for pink Z2 part number. So if you open the AMD website, we can see that pink Z2 is featuring the Zinc XE7Z0201 CLG400C. That is the part number of the chip, right? That is the name of the chip that I am using. So you can directly search for this particular chip number and you will be able to find it in the Vivado parts. But if I go to parts and search for this particular, I can search for this particular part number and I will be able to find part number is XC7Z020CLG. So you can see that the part number is available. So the part number says a lot about what kind of chip I am working with as. So XE stands for Xilinx chip 7 series, Z stands for Zinc architecture 020 is 7020 series of the Arctic's chip. Okay, CLG 400 is going to be the number of input output pins. So you can see here that the number of input output pin count is 400. That describes what kind of chip I am working with, what are the available resources, and you will have all those information here. So you will be able to see how many LUTs do you have, how many flip flops do you have, how many block RAMs do you have, and all the available resources are mentioned here. What is the difference between using a part number and using a board file? So using a part number, you have complete access to the particular chip and its input output peripheral, but you do not have all the peripherals that are added on the board. Only the pins that are there can be accessed, right? But if you, just to make things easier, we can have something called as a board support package, which also includes all the peripherals on them. I have, let's say, HDMI port in and out. 2 HDMI ports are available. Okay, so those 2 ports are obviously utilizing some amount of IO pins on the chip. That is not directly available to me when I use the part number. So if I want to target this particular HDMI, I need to search for the HDMI datasheet for PingZ2, understand which input output pins are connected to my chip and the HDMI in, HDMI out. I need to assign those particular pins to work on this particular HDMI port. But if I have a board support package, BSP, this is already mentioned there. This is already mentioned saying that, okay, these are the pins that are connected to this peripheral. It can be anything, not just HDMI. It can be buttons, it can be switches, it can be the Ethernet port, the power supply, everything. That is directly available. So how do I access the board support package? How do I add this particular PingZ2 onto my tool? They are going to be the speed grade. -3, -2, -1 is going to be the speed grade. You have a particular design, right? So once you start with a design, you will have an understanding of what is your requirement when it comes to resources. So how many LUTs do I need? What kind of IO pins do I need? Do I need some kind of sensors, right? All such information is available to you. So based on that, you can decide on what is the FPGA that you're looking for. So this is completely like project oriented, but you can see what is the packaging that you require. So do you need thermal shielding? Do you need radiation shielding? If you are preparing a chip, if you are working on a design that requires a chip that you are sending it to space, then you need to have thermal shielding, you need to have radiation shielding and multiple other things. If you are sending it on a submarine, or if you are directly dumping it into the ocean to track the ocean waves, right, then you need waterproof. So all those kind of things are required. So you can search in what is the category that you want and what is the packaging that you will require. Packaging means how many IO pins are required, what is the classification of that particular packaging, and what is the temperature grading. So all these are available. So if you haven't already decided on what chip to use, you can also figure it out in that way, right? Put some filters, say that, okay, I need this many IO pins, I need this. I've already told you one thing. If you are directly using only the part number, okay, all the peripherals are not there. So let's say you are using the same chip, right? You have 400 IO pins. You can connect all the 400 IO pins to one set of sensors. You might not require HDMI. You only require some sensors input and board part 0 preset, okay, one image. So this is the board support package. These are also called board files. So where do we need to paste this so that the tool will pick it up? So you can go to this particular path where you have installed Vivado, where you have installed Xilinx. Should mostly be in C drive under the folder called Xilinx. Inside Xilinx, you will be able to find Vivado. Create a new project. In the quick start menu, you will have the option to create new project. You can skip the welcome page, click next. Now you can assign a path and a project name. Please make sure that there are no spaces anywhere, neither in the project location, project path, or in the project name. Okay, people who are working on the Linux system, it will give you a path that is in the root, /home /Xilinx /Vivado /2023 dot something it will give. Path will not work because it is a root path. So select a path that is not root. Somewhere in the desktop, you can create your path. Make sure there are no spaces, that is one. And make sure your location is accessible. Once you have done that, click next. When we want to work on developing an FPGA based designing, okay, there are multiple things that you need to consider. Okay, it's not one simple straight way. So one is you can start right from the scratch, create your RTL, develop your design, okay. But if you are a verification engineer, okay, so you will be using the tool in a different way. If you are a timing analyst, you will be using the tool in a different way, okay. If you are only working on IO pin planning, okay, you don't require the whole design, you just have to work on IOs. What are the pins and what is my board design? You want to work on that. So there is a different way of working with the tool, okay. So that is what is given here. The project type will describe how you want to work with the project. So if you are an STA engineer, a timing analysis engineer, okay, so you will be working only post synthesis. You will not be worried about the design. You will be worried only about what is happening after the synthesis. So there are multiple ways where you can work with the tool. So for our understanding, we will be using only RTL based project. For our benefit, we will be selecting RTL project, and the second thing is we will also select the option do not specify any sources at this time, okay. It is not mandatory that you do this, but just for the convenience, just for our understanding, we will not specify any sources here, we will specify them later, okay. We will add sources separately. So you can click next, and here comes the part where we can select the particular part number or the board directly. Most of you have already installed the pink board, okay. So you can go to the boards tab, not the parts tab, go to the boards tab. In there you should be able to find pink, okay. You can directly search for it. What we have seen until now is only one way of adding the board, okay. There are multiple ways to add the boards, okay. If you see my screen, the pink ultra scale plus ZU board is not added, but I have an option to download. I can directly install the board here also. But the issue might occur that there could be some firewalls in place in the university or in your colleges, wherein you will not be able to download these packages directly. That is the reason we have manually added the board. But if there are no restrictions, you can directly download as well. So you can select the Z2 board, pink Z2, that is what we will be working on, and click next. You will come to the summary page. Select the board, click next. There you will be able to see what is the default board that you want to work on, what is the part number assigned to that particular board, which family does the board belong to, what is the IO pins that are available on the board. You can see all of those information. That is the summary. Once you are here, you can click finish, and that will start creating a project. So speed grade is something that depends on the chip at so there are grades at which a chip works, right. It depends on the technology on which the chip is built. Right now we do not have that option. We are using that is all, what is already given to us. What is happening with my project at a glance can be read from project summary. You can see the boards that you have added, right, which board you are working on. If you scroll down, you will be able to see the synthesis, implementation, DRC violations, timing reports, utilization, power reports. As of now there is nothing, but you will be able to see those, okay. At a glance you will be able to understand what is happening with your project. And next comes the bottom tabs that are going to be the TCL console, messages, logs, all the reports, design runs, and most important of all is going to be our extreme left column, that is going to be the flow navigator. For working with FPGAs, there are a few steps that we need to follow. The first thing is we need to add our design. Either we can create it directly or we can simply add it there. That is one. The second thing is we need to verify if our design works in the way that we intend or not. That is called simulation. Step 2 is simulation. Step 3 is going to be synthesizing our design with respect to the technology that we are working with. That is step. Step 4 is going to be implementing our design onto the chip, which includes place and route of our design. And the last step is converting all this data into a file that the board can understand. So that is going to be bits. So again, the flow is in this way that you add your design, whether you type it in or you add directly a file. Second thing is understanding how my design works functionally. Is it working the way I intended to do? Third step is to synthesize my design, which is converting the RTL based design into something that can be worked on the FPGAs, right. So in this particular case, we will be trying to convert it into some form of data that can be placed on the LUTs. So LUTs in turn stand for lookup tables, right. Why do we call them lookup tables? We have an AND gate. We all know the functionality of an AND, but we cannot replicate an AND gate directly on the FPGA. Then how is it working? Then how is that an AND function is happening on the FPGA? So what we are doing here, when we say we are coding the LUTs or we are putting the logic onto the LUTs, so we are saving that data onto the LUT. Okay, whenever there is a function that calls for the logic of AND, FPGA is doing is looking at this particular data that is stored, which is the truth table. It will see what are the inputs and it will compare it with the data that is already stored on the LUT, and it will directly say, okay, 1 and 1, okay, this is 1. It is directly taking the reference that is stored on the LUT and giving you an out. The simpler example is AND gate. It can be as complex as we want. We will understand with an example how this is getting translated and why it is getting translated. For that, we need to add a particular source. You have already downloaded the source files, right? So ping Z2, there is one folder. Inside that, there is a lab1 folder. So inside lab1, you will be able to see 3 files. One is a simple lab1.v file. One is lab1-pink, which is the XDC file. Sorry, underscore pink, which is the XDC file. And the third one is underscore TB. So back in your Vivado tool, you can open the Vivado tool. You can click on add source. There is an option to add source. Plus button is there inside the sources tab. Here we have 3 different types of sources. One is a design source, one is a constraint source, and the third is a simulation source. The first thing we need to add is a design source. The second is going to be a simulation source, that is for functional verification or simulation of our design. And the third is going to be a constraint, that is going to assign the ports to the pins on the board. Ports in our design to the pins on the board. That assignment is called constraint. Okay. So first thing, we'll add the design source. Click next. You have 2 options here. One is to add a file or to create a file. So you can do both. For the convenience, we are just simply adding a file. Click on add file and go to the particular location where you have saved this lab1.v file. Now inside the sources tab, if you expand the design sources, you will be able to see lab1. We're directly assigning our outputs to an input logic. So the first thing we'll try to understand is how is this particular HDL code being read by my tool. In the flow navigator, you will be able to see RTL analysis. So inside that, there is an option for open elaborated design. Click on open elaborated design and click OK. This should open our design translated from the HD. So that is our gate level design. Simple translation. So this is our design. Okay. So the next thing, sorry. Now what we'll do is we'll try to simulate our design. So we all already know that we can force our input. In the design, we can force constants, force our inputs and understand what is our output. But it is very cumbersome when it comes to high-end designs with a lot of input. So that is where a test bench file comes in. A test bench file is a set of scenarios that you want to test. Test cases, you can say. Okay. A bunch of test cases will be added onto a file to run over our design. So you can go back to sources tab, add source. This time, rather than a design source, select simulation source. Simulation source, click next. You can add the file called lab1_tb. So once the test bench file is added, so after updating, the test bench file is added. Next thing is we can click on run simulation. In the flow navigator, click on run simulation. We'll have the option to run behavioral simulation. So I can expand this and click zoom fit. There is an option to zoom fit, 4 arrows. Now you can expand the buttons and the LEDs, which is input and out, and you can observe what is happening with your design. So this is our desired output. You can only expand buttons and LEDs, not the intermediaries, not right. So this is the simulation and this is my expected output from my design. Once I'm satisfied with this, I can close the simulation part. The next step is going to be synthesizing my design. So there is an option directly available to us to run synthesis. The advantage of using Vivado tool is that you can directly jump ahead and generate the bitstream file. The tool will automatically take care of the process by itself. Okay, it will run the synthesis, it will run the implementation, then it will automatically generate the bits. Okay, you don't have to do it manually every single time. If you want to understand something in the middle, if you want to get some reports, then you can go step by step. If not, you can directly click generate bitstream and it will directly go and generate bitstream through following the processes of synthesis and implementation. right. So, for the sake of this example, we will run synthesis, click OK, select the maximum number of jobs, click maximum. Yeah, it depends on the system that you are using. Select maximum, click OK. So, once you have clicked that, we can observe what is happening with the tool in the design runs tab. Okay. So, my synthesis is running here. Okay. And if you scroll, okay, let us not do it right now, but yeah, once the synthesis is completed, you can scroll and see. Yeah. Yeah. I am coming there. So, my synthesis is completed, and inside synthesis I am able to see a part of my resource utilization, right? How many LUTs are being used, flip flops, what is the amount of RAM being used. Okay. So, what exactly is synthesis? Okay. So, once the synthesis is completed, you can click on open synthesized design. Okay. It will ask you to close the elaborated design, click yes. It's okay. You can close that, sir. For now, you can close it. Cancel. Yeah. Okay. Now click on open synthesized design. Once you click on once you click on open synthesized design, either you will get the device view or the package view. Okay. Device view or the package view. Okay. We will come to this in a bit, but there is an option called schematic. Under the open synthesized design, there is an option for schematic. Can you click on that? Yeah. Right. Everybody is here? Do you want me to wait? So, if we look at the schematic, okay, what we are seeing here is similar to what we have seen in elaborated design, but in the elaborated design, it was giving gate levels. So, it was giving gates. Rather than gates, once I synthesize my design, what it has done is it is giving me LUTs. Right. So, earlier I have told you that you need to store the gate level data onto the LUTs. You cannot directly implement gates on the FPGA, but rather what we are doing is we are implementing the logic on the FPGA, right. We are saving that logic onto the LUT. So, here we can see that we are using LUTs rather than gates. Okay. Here we are seeing LUTs rather than gates. Okay. And to align with how the FPGA works, we also have buffers. Sir, because in real time we will be working with clocks, right. To synchronize the data, we need buffers.
But we not use clock.
No, we are not using clock, but are we giving, we are not also giving direct current, no. We will be using alternating current. Two more things that we need to understand at this point. Okay. One is the package view, one is the device view. Okay. In the device view, you will not be able to see anything right now. If you are not getting the package view, not a problem, you are in a different layout, that is it. Okay. So, at the very top right corner, you will be able to see the layout. Okay. Here I am in IO planning. Okay. You can click on IO planning, then package view will open. What we are seeing here is we have the lab1 file where I have a specific set of input ports, output ports, right. But how do I assign these to my physical hardware? Because if you see the schematic, right, my logic is getting translated onto LUTs. Okay, I am happy about that. How do I translate the inputs and the outputs? The input ports and the output ports. Okay, I need some kind of physical connection there, right? That is what is happening with the package view. Again, there are multiple ways to work here. We'll be looking at two different examples. Okay, we'll be following one, but we'll be looking at two different examples. Okay, so I told you at the bottom you will be able to see IO ports. In that IO ports, you will be able to see all ports, and there are buttons and LEDs. You can directly assign those ports using the GUI here. Right, you will be able to see IO standard, default, package pin. There are multiple columns for that, right? IO standard, package pin, all those are available. Our FPGAs in 7 series work in between 1.8 volts and 3.3 volts of maximum voltage. So we need to assign them according to how they have been derived. Based on their data sheet, you need to assign them. Either you can do it manually or you can directly assign them here. Okay. How do I know what pin is connected to which peripheral on the board? That is the big question. So you can just search on the Google for something called as a master XDC. You can directly search for ping Z2 master XDC. So XDC stands for Xilinx Design Constraint. XDC stands for Xilinx Design Constraint. There is a GitHub link here. You can open that. lab1_ping. There is one file here. Right? So that is the XDC file _ping, not Spartan. You are in the Boolean board file. Come back, go to ping Z2. So do not worry about downloading that file. It's okay. I'll tell you two different ways how to work with that file, without that file. You can look at my screen here. What the file contains is consolidated only to this particular example that we have. Okay. But what I'm showing here is the complete XDC file for Z2 board. Okay. They're basically the one and the same. What my constraint file tells me is how do I assign the pins on the physical board to the ports in my design. In the file, there is only buttons and LEDs because that is the only thing that we are using. Okay, but this is a generic XDC file. Okay, what is here is it says set property direct connection. What is the IO standard of that direct connection is LV-CMOS 33. Okay, this is already recommended by the manufacturer. And what is the pin number that I am assigning is package pin D19 to where am I assigning it to, which port am I assigning it to is get ports, and inside flower brackets I will give the port name. In the file that we have already given, it says LED 0 or button 0. Okay, but here it's just stating the name. We can directly copy paste this particular sets of instructions and we can modify it to work for our design. That is one way of doing it. That is the file that I have already given you. Okay, you can directly add that file and you are done. Okay, or if you want to do it manually, what we can do is at the bottom we have IO ports tab, right? So even if you do not have that file, not to worry, we can manually do it. Okay, so how do I do it is assigning them here. Using the IO ports tab, you can expand the buttons. You will see button 3, button 2, button 1, button 0. You are able to see button 3, button 2, button 1, button 0 once you expand the buttons, right? So in the package pin, you have the drop down menu. Under package pin, you have drop down. So you can check the XDC file, master XDC file, and find out which pin is connected to this particular button. So you can open the master XDC, see that the button 0 is connected to pin D90. Button 0 to pin number is D90. So what I will do is button 0 is connected to D90. IO standard that it is following is LV-CMOS 33, which is 3.3 volts maximum voltage. Yeah, we need to change. We need to change the IO standard and the package pin number. No, the button 0 is D90. Similarly, we have button 2, that is D20. Button 1 is D20. LV-CMOS 30. Yeah, button 2 is L20, button 3 is L9. Similarly, we need to assign the LEDs as well. LEDs are the outputs here, right? So we need to assign the LEDs as well. Once we have assigned all the pins and the port, you can click save, Ctrl S. It will ask you to save the constraint file. Click OK and give a name. Let's just say I am giving lab_1_xdc and click OK. once you have saved that particular constraint file. So if you go to sources, not required, it is going to be under the sources constraints, you will see a new file generated. Okay, if you open that file, it is similar to what I have already shared with set property package pin, so and so package pin is assigned to get ports of so and so port in my design. So either I can directly copy that and edit it, copy paste, you can add it here, that will also work, and that will generate a file saying the same thing. Once I have my XDC file and the design file, I can move forward, again run synthesis and implementation. But we are not going to run synthesis again. Click on run implementation. There is a pop-up now. That pop-up says synthesis is out of date because you have added a new XDC file. Your old synthesis is out of date. You have new information to synthesize. Okay. So what you can do is you can directly say yes and click OK. It will start running the implementation. But it's not only running the implementation, it is running synthesis again. How can I say that? You can go back to design runs and you can see that synthesis is running, not implementation directly. So that is the advantage of using Vivado, because it will run the step that is necessary, though you have chosen a step further. Okay. Even if I click bitstream, generate bitstream, it will again run the synthesis, implementation, and then it will generate the bits. So does anybody have any questions until this point? Earlier we have seen two different formats, right? One is package and one is port. So I am just coming back to this package. Why? Because this package is what is telling how do I assign the ports. That we have already done, IO ports, right? IO pin planning we have done. So this package view is what is letting us assign those ports. If you go back to default layout, you will be able to see the device. It will be similar looking to this particular. In this particular layout, I have a few highlighted options. These are the LUTs that are selected. So these are the LUTs that are selected. I can zoom out. I can also see the assigned inputs and output along with the buffers that are assigned. So what is happening after I run the implementation is that my design is getting translated onto the device with placement and routing. PNR is happening. Okay. Placement and routing. So it is placing where each cell and each net of my design needs to be, and at the same time it is telling how do I route this design, where do I place it to get the best optimal result, right? All of this is dependent on the methodology that you are using for implementation. There is a whole another subject where we are discussing about the methodology. The tool will select which is the most optimal location and for both placement and routing of my design. It is selecting on its own and it is giving me an out. So once I have implemented the design, the next thing I can click on generate bitstream, click OK. Before I move on to the board, we need to understand a couple of things. If you have the board in hand, you can go ahead. If not, look at the screen. Okay. There are two things that we need to understand before moving on to working with the board. So most of the FPGAs can be programmed in multiple ways. There are different ways you can program the particular board, and there are multiple ways how you can power the board. So even in this particular board, you can see there is a micro USB cable along with the power port available. DC adapter is available. So how do I select these things? How do I select how is my board getting powered? Okay. Right next to the buttons, there will be a small jumper. Right next to the switches, there is a jumper available. We'll select the power from either external source or the USB. How do I boot the board? Is right next to the HDMI port, between the PMOD and the HDMI port, I'll be able to see the boot mode selected. There are multiple modes, as I've told you, the board can boot from. This particular board can be booted using the JTAG cable or the onboard memory USPI or the SD card. Okay. 3 modes are available. So you need to put the jumper for JTAG mode, because we are directly going to dump the program from our system. We need to set it to JTAG mode, last two horizontal, and the board will be powered directly from the USB port. You can now connect the board to your system. Do not turn it on right now, I'll tell you. Turned on the board, there should be one red LED, that is the power LED. So once you have connected the board, the board is on. Now you can click on open hardware manager. Under generate bitstream, there is an option to open hardware manager. Click on open hardware manager and you will be able to see no hardware target is open. You have the option to open a new target. Click on open target. There are two ways to connect to the board. Okay, one is manual, one is automatic. You can always go for automatic. Auto connect the board. Once you auto connect, it will look for whatever the hardware is connected to this particular PC, and you can see in the hardware tab. So here you'll be able to see it's a Xilinx based chip. Manufacturer is TUL. TUL is the manufacturer. If you scroll down, you can see which version of the chip is connected. XE7Z020, which stands for Zinc 7020 chip. Even on the board right above the chip, you will be able to see Zinc 7020 on the board. So once you confirm that the right chip is connected, you can click on program device. Sir, you can click on auto connect. We have the program device. You can click on program and you will be able to see the board flash the done LED. We are working with an SoC, which is system on chip, right? We can also target the processor. So how do we do that? And we'll try to understand what is the architecture that we are following. We'll start off from there. So what we have seen in the morning is a pure FPGA fabric. How is the architecture there? The second thing is going to be understanding how a Zinc chip is designed. We have seen that Zinc includes a processor. There's a processor on top of the FPGA fabric, that is Zinc. What is the advantage of Zinc? What is available to us when we talk about Zinc? When we talk about Zinc, for the most part, we have a ARM based Cortex A9 processor available to us. That is in general I am saying. Not every board will have the same specifications, but most of the boards will have the same specification. For the most part, we'll have a dual ARM Cortex A9 processor available to us, along with the memory that is required to run it, by which I mean the cache memories. We'll also have the IOs required, okay, and we'll have generic IOs running between the FPGA and also the processing system. So the processing system in short is PS, and the programmable logic, which is the FPGA fabric, is called as PS. When we look at the architecture, we have a dual ARM Cortex A9. There are a few boards that come with single ARM Cortex A9 processor also, but for the most part we'll be looking at dual core. ARM Cortex A9, it comes with a 32 kilobit level 1 cache. Each core has 32 bits of inbuilt cache memory, and we have a generic level 2 cache of 512 kilobits, and we have dedicated memory units available, which is 256 kilobytes. Okay, this is purely to store data, and we have inbuilt timers and counters and interrupts available if you want to generate an interrupt. So you can directly add those, but there are a few limitations, but they are available. And along with that, we have an FPU engine. This FPU engine will help you to do real-time processing. FPU stands for floating point unit. So that will help you to do real-time processing as well. But most important thing here when we talk about the processor on board is that every single connection that is happening, that is available to us, is always running through something called as an amber switch. AMB. All the communication that is happening in and out of the processor is running through an amber switch. Along with that, we have multiple peripherals that are in sync with our processor. We can add memory units, we have NAND NOR memory controllers, static memory controllers, okay, and we can also add whatever. There are multiple protocols that are available to us that we can choose from. We have SPI, we have I2C, we have CAN, we have UART, we have DMA, we have USB, we have SD, and we have gigabit Ethernet. All of these connections are running through a MUX. All of these are running through a MUX. So therein falls our limitation. This MUX is only a 54-bit MUX. We will eventually run into a problem if we are using all 54 ports of my MUX. How do I extend it? If I want to add more ports for communication, how do I do it? That is where we have the flexibility of EMIO, which is extended MUX input output. MIO is going to be 64-bit. 64-bit MUX is available, and you can extend it with another 64. So you can extend it using EMIO. EMIO is running through the FPGA, and one of the most crucial parts of our processor is going to be SCU, which is Snoop Control Unit. that is going from the processor to the PL, right, PS to PL, and then we have slave reporting back from PL to PS, right. But there is one extra, there are multiple types of ports. There are high density ports, there are high performance ports, there are high range ports. Depending on the board that you are choosing and the application that you are working on, you can choose between different kinds of ports as well. But there is one specific port that is called as ACP. It is in slave AXI ACP port. So that particular ACP port is going to help you to accelerate your design. So the port specifically is called ACP, which stands for Accelerator Coherence Port. That is porting your design into an accelerator, and the SCU, Snoop Control Unit, that we were discussing is going to help synchronize the design with your process. That is like a synchronization circuit and your accelerated design on FPGA. If you have already opened it, you can close the project, file, close project. We'll create a new project. We'll start with a new project. Okay. One is what we are going to see right now is through Vivado and Vitis. We'll use both these tools to create a design and dump it onto the board. Other than this, we have already discussed something called as ACP port, right? Acceleration Coherence Port. So you can also use accelerated designs using multiple other ways. Okay, you can get it from MATLAB, you can get it from Vitis HLS, high level synthesis. Okay, there are multiple ways to create a complete system, embedded system. Okay, this is one way that we are going to look. So rather than adding sources and using HDL files, what I'll do is I'll create a design using IPs. There are two ways to do it. Again, even if you are working with HDL, you can integrate those IPs using IP catalog. If you are working in HDL, you can use those IPs. If not, you can directly create a complete IP based design using IP integrate. There are two things. One is IP catalog for HDL based IP designs and IP integrator for pure block design. We'll create a new block design, create block design, there is an option. Click on that, you can give a name. I'm just naming it as ESD, Embedded System Design, and click OK. So what we have here is our block design. What we need to do is start adding blocks. Either you can go for Control I, or you can click on the plus button here, add IP, or there is one more plus button at the top. Click on that and you will have a list of IPs that are available in general and also for the specific board. That is why we need those board package files that we added in the morning. This is why they are required. If you are working directly with the chip part number, you will not be able to get some of these IPs. Some IPs are specifically created for the board, right? Those IPs will not be available directly for the chip. What we'll do is we'll add a processing system. Okay, you can just search for Zinc. Zinc 7 processing system will come up. There are two different sets of IPs here. One is specific to the board, one is generally available in Vivado. So the board specific IPs are a part of the package that we added in the morning. Once we add that, all the IPs will be directly available to. This particular Zinc processing system, even if we go with the part number, for some boards it will be available as a generic processing system, not specific. For some boards it will not be available at all. Those kind of issues will come up if we do not add the board files. You can double click on Zinc processing system and that will be added onto our block. There is something called as designer assistant and it is asking you to run block automation. You can click on run block automation and there is a pop-up that comes, right? This dialog box comes. The advantage of using these IPs, okay, is that we have direct access to design and modify our design. How was it? Is what we just see. Running the connection automation, already selected what are the available resources in my design and what connections can be made directly. Okay, we just ran it, but we'll run it again, then we'll understand. But that was a dialog box. Provide all the connections within our design. We'll run with a small example first. So what I'm trying to do is I'll try to ping the processor. I'll just try to ping the processor, run a small program on. I'll just turn on whatever is required for me. So right now what we are seeing is a complete processor. I don't need a complete processor. I want to customize what is available to. How do I customize? Double click on the Zinc block. That opens the recustomization dialog box. All the components that are available to you that you can customize are in green color. Whatever is needed I'll customize that. The first thing is PSPL configuration. We'll go one by one, okay? PSPL configuration. You can expand the general tab. You'll be able to see clock resets and clock triggers. You can turn off the clock reset. Inside general, you will be able to see enable clock resets. You can turn it off. The next thing is I don't want any kind of communication between the PS and the PL. Okay, you can expand ASI non-secure enablement and you can turn off the master GPIO. AXI non-secure enablement, underneath that you have GP master AXI, you can expand that. Inside that you have MAXI GP0 interface. Okay, you can turn it off and leave only the UART 0 on. So you can see here all the list of connections and protocols for communication are available to me direct. You have quad SPI, SRAM, NAND flash, Ethernet, USB, SD card, SPI, you have UART, I2C, CAN, TTC, GPIO is also available. Here we only UART 0 is required, rest everything you can turn on. You can click on OK, you can ignore the warnings. Quickly running through it again, double tap to open recustomization window. First thing PSPL configuration, general, clock reset, you can turn off the reset, expand AXI non-secure enablement, you can turn off the master GPIO, AXI GPIO. Next, in peripherals, we are turning everything off other than the UART 0. And then in clock configuration, you can turn off the PL fabric clock. Then click OK. This is what you will be left with. Usually while designing an FPGA, what we do next is we try to run the simulation, then synthesis, then implementation, bitstream generation. That is the usual process. But here there is a small change because we are using IPs and these IPs are pre-built IP. We are not designing them from scratch. We are taking an existing design and modifying it. One thing that changes here is before we go for synthesis and implementation, we need to create something called as a wrapper file. So wrapper file is like a carbon copy of the design that we have done so that we can overlay it on top of the existing hardware and we can match out the components. So how do we do that? In design sources, we have the .bd file. You can see here on screens in the sources tab, .bd file will be available. That particular .bd file is the block design file that we just created. We need to create a wrapper of it. So what we'll do is we can right click on it. So we right click on the block design. Okay, we are able to see multiple options here. Two things we'll do is create the wrapper and second thing is generate output products. Okay. So what is wrapper we have already seen. What is generate output products is because this is a pre-built design. The logic inside a design is not going to hinder a design. Okay. The only thing that we care about right now at this point is what are the inputs and the outputs, what are the ports that are available to me. Why is it important? Because we already have a pin planning assigned to this particular IP. So in the first half we have seen how do we design and we only talk about the ports in the design and we need to give manual connections to the package pins. But when we are using IPs, those connections are already made. We don't need to manually assign them again, but we need to take care that the logic is not the most important at this point. Those connections needs to be solidified. Okay, that is what generate output products is doing. Click on generate output products. We'll have three different options. You can do that, sir, not a problem, but you can go for output products first and then generate HDL wrapper, not a problem. So we'll have three types of synthesis available to us for output products. One is global synthesis, one is out of context per IP block, and the third is out of context per block design. So we'll be selecting out of context per IP. Global synthesis will run generate output products for the complete design, irrespective of if it's already done or if it is out of date. Out of context per IP is only going to take care about a particular IP that we're working on. Okay, each IP will be taken into consideration. The same thing for block design, it is going to take the complete block design into picture. So we only have one block design, one IP. So out of context per IP and click generate. Select the maximum number of jobs, click generate. Now you can again right click on the block design, create HDL wrapper. There you will be able to see two options. One is generate wrapper that the user can edit, or let Vivado manage the updation automatically. We'll select the second option. We'll let Vivado manage the wrapper and auto update. Click OK. So once your wrapper is generated, it is going to be a .v or .vht file. If you open this .v file, you'll be able to see the complete processors. So once you open the .v file, you will be able to see the instantiation file for the process. We are not going to use that as an instantiation file, but just for our reference, we have that as an instantiation file, and that is the wrapper. That is the carbon copy that is sitting on top of the hardware, right? A design is embedded and it is on top of the hardware, right? So that we are not using any peripherals or any available resources on the board. We are only targeting the process, purely the process. So we are not going to generate bitstream, but rather we'll take this particular wrapper file, which is only targeting the processor again. We'll take it into Vitis and we'll try to program the processor there. So how do we do that? Click on file, and at the very bottom you'll be able to see export option. We have an option to export it as hardware. We'll export the complete hardware. Click next. We have two options for our output here. One is pre-synthesis, one is including the bitstream. So the output options is pre-synthesis and including bitstream. Right now what we'll do is we'll exclude the bitstream because we are not working with a complete bitstream, right? So we'll exclude the bitstream and we'll only select pre-synthesis. Click next. It'll ask you to create the name the file, the wrapper file. So it's already given a suggestion. I'll just not change it. I'll just click next and finish. So go to the location where you have saved this file. Okay, there you will be able to see _ wrapper file. Okay, this is the wrapper that we just generated. In the same location, create a new folder and name it as Vitis. Inside the tools menu, you have an option to launch Vitis IDE. It will ask for a location, workspace. Okay, so please give the same workspace that you have created right now. You have created a folder called Vitis, right? You give that location there. Launch Vitis IDE. Once you launch the Vitis, it will ask you for the workspace. You need to give it a location. So that location you give the same folder that you just created. The reason why we need to do this is because Vitis creates a bunch of supporting files again. So if you leave it in one location, then your workspace will be corrupt. So if you launch a different project, it will create the same set of files again, okay, and it will say that it is corrupted. So that is why it is better to create a separate location for every different project that you are doing. So once you have given the path, you can click on launch. In the terminal, there is one option. The first option we see is to open a terminal. In that, the first option is to open a new terminal. You will be able to see choose terminal. You can select serial terminal. So we have local, SSH, Telenet, serial. You can select serial, and you need to have the board connected for this. Connect the board, turn on the board, selected the port. Next thing is you need to set the baud rate. The baud rate is going to be 115200. For any of the FPGA boards that you are using, it's going to be 115200. To use any different serial terminal, I'm using Teraterm here. You need to select the port, okay. Click OK. I will go to setup serial port 115200 is what I am using. Okay. So once I have that, the next thing is I can directly run the application on the board. How do I do that? Right click on the application, run as launch hardware. So this is one option that we have. So it is dumping. Here you can see it is dumping the program. So you can see Hello World successfully ran the Hello World application. Okay. So you can try the same thing on Linux using something called as an emulator. How do you do that? Sir, right click on the application, run as launch hardware. So run as launch hardware is one option, and in Linux system, if you are running the same thing, instead of the complete design, you can only select the application, right click, run as launch on emulator. There is an option called launch software emulator.